Okay, this will be one quick little video on question 16, the first of the short answer questions in the test. Rightio. Now, I was hoping this would be pretty easy because we did it the day before. Both classes did it the day before. But everything you needed was in the question anyway. But really, what provides the torque? What's making this thing spin, right? Now, what do we know? This thing spins about this axis. So many of you said it's this radius up, that mass provides the torque. No, that's experiencing the torque. What provides the torque is this piece of string that goes over here and is tied to this mass, which is mg. So it is the, the weight of, little mg, or, tension, because that's labelled there as T for tension. That's what's causing the force on this spool here, right? This spool here is what spins. Why? Because there's a string attached to it and it's making it spin. If you looked at it from above, it would be in a clockwise direction. Then the student recorded this data, right? Small m, 55.9 grams. Big M, 273 grams. So this thing here was 273 grams. Right, and then we've got these screenshots, okay? And I doctored these to really make it clear what these are, right? You can tell this one, run one has the lowest slope. This is angular speed against time. The slope of angular speed against time would be angular acceleration. So in both of these, m on that linear fit is going to be alpha, the angular acceleration. Agreed? Agreed. Right. So the one that has the lowest acceleration must have had the greatest moment of inertia, and vice versa. Just like if you have a constant force, the one with the biggest mass would have the smallest acceleration, and vice versa. Rightio. B. Calculate the torque applied. Now, we agreed, or I agreed anyway, that the torque is provided by the little mass, right? So little mass mg, that's its, and then times the little radius, which is 1.25 centimetres, so 1.25 by 10 to the minus 2 metres. Back to the diagram there, it was, I'll rub that out because I've crossed it out there, but little r is this little radius here, sorry. That little radius there. The radius of this does not matter, okay? The radius here matters because that is where this tension force is acting, and you are given that as 1.25 centimetres. Big R, 21 centimetres, is that distance. That's 21 centimetres. The distance between the big removable mass and the axis of rotation. Here we go then. So, if I continue working that, so it's 55. Now guys, this is in grams, so I've got to convert it to kilograms by 10 to the minus 3. Let's go by 9.8, and then 1.25 by 10 to the minus 2. And you should get, I reckon, 0.00685 Newton meters, which is the unit for torque. Okay, which run corresponds to the rotating beam? Well, the one with the, you've got to think about the rotating beam without the mass attached. That's the one with the lowest overall moment of inertia, so it would be the one with the greatest angular acceleration, run 2. 1 mark for saying run 2. 1 mark for sort of discussing the fact that greater slope and therefore larger alpha as torque equals I alpha or something like that. These things, those two guys there are inversely, inversely proportional to each other. If one goes up, the other goes down, right? Inverse proportional if this is a constant. And that was a constant for the whole experiment because we didn't adjust the small weight. Question D, rightio. Use information provided, there's a clue kids, to calculate the moment of inertia of the rotating beam with and without the mass. Okay, so let's talk about run 1. What do we know about run 1? Well, we know torque is I alpha, so I is torque over alpha. We've already worked out the torque. We can get alpha from the data from the graph. Sorry, 312. 312. And that moment of inertia is 0.02196, and the units are kgm squared. For run 2, what do we find? It's the same torque, don't forget, 0.00685, and we're dividing by the alpha. In that case, we're 0.556, and we get 0.0123 kgm to the m squared. On this one, I made units 1 mark, so if you got perfectly right without the right units, I only gave you 5. So not a, hopefully when you see this again, you'll just smash that question out of the park. A lot of you lost all those marks. Okay, E, what was the moment of inertia of the mass alone, guys? Well, you subtract one from the other. That's how moments of inertia work, and that's how we did it in the experiment the day before. So 0.00966 kgm squared. Happy times. Now, calculate the expected value for the moment of inertia. Well, the expected value, you go to your data sheet and say, right, well, the expected value of just a mass spinning at the end of a string, because there's no beam there. If the mass was on its own, what's the moment of inertia of that mass on its own? That would be equal to, the data sheet says mr squared, and in this case, the mass was given as 0.273, it was 273 grams, and I'm converting it to kilograms, and that is the radius with which it was spinning. We're talking about the big mass. A lot of you put the wrong radii in at different places, so that's the radius of, let's go back to here, that's the distance it was from the axis of rotation, yeah? 0.21 of a centimetre. All right, back to here, smash that out, and we have got a value of 0.011 kgm squared. Now, all I'm doing is subtracting one from the other and dividing by the biggest value, but the difference between what we expected and what we got, what I got anyway, and you should have if you did it the right way, is 0.137, and we are within 12 or 13%. Okay, I'm going to stop that video because I did it without making a mistake, and I will do the next question. I'll see you on the other side. Bye.